Hi, so in this video we'll make our first deep neural network using Keras, and we'll use it to classify digits. So we'll be using this dataset called MNIST, and it has images with digits from 0 to 9. So we'll make a simple neural network model with Keras and try to classify the digits. Let's see how it goes. So first we need to import few libraries. So let's import Keras, then let's import matplotlib as well. Import matplotlib plt, then let's import numpy as np. Then I'll just set this to inline, and just so you know, you can see my Keras version. So my Keras version is 2 point something, so make sure that you have at least the major version same as me. The dataset that we are going to work with is already provided with within this Keras library, so we can just import. So for that, from keras.datasets, import MNIST. Then if we look at the functions load data and see the help, we can see we need to provide the path if we need to, otherwise the main point of interest is this one. So returns a tuple of numpy array in this format, so let's just copy this one and equals to load data. So if you're running this function for the first time, this mnist.load data, then it will download the dataset from the internet, otherwise it will cache it in your some directory, I don't know where, but yeah, it will cache it and then load it from your computer instead. So now that we have our training data and the testing data as well, let's just see what we have. xtrain.zip, then ytrain.zip x. So we see that xtrain contains 60,000 samples of two-dimensional. Each sample is a two-dimensional array or matrix of size 28 by 28. So in our case, because these are images, so these are images of size 28 by 28, and these are black and white images. Similarly, we have for the labels, we have 60,000 labels. For testing, we have 10,000 images. So yeah. Before we do anything, let's write a simple function to plot these digits, and so that we can visualize some of those. Let's call it plot images. For this, we'll supply images and labels. Then we'll print 5 images per row. So number of columns will be minimum of 5 or len images. So at least if we supply less than 5 images, then yeah, we choose the minimum of that, but again, never mind. So the number of rows would be then images divided by n. So this double slash means do the integer division instead of normal division, so this will always return an integer number, an integer. So let's plot that figure, then for I in range. This is just for plotting. I mean, we don't need to go through this specifically. This is not our main focus for this tutorial, but then n rows. We create subplot for each image, then we turn off the axis so that the numbers in the x and y axis they don't show up because we're just plotting the image. And then plot.im show image is I. Then because these are grayscale images, let's set the color map as gray. Then subplots, title, let's set the title to whatever labels we supplied, and finally plot.show should do the trick. Now what we want to do is plot some random 20 images. So for that, to get the random indices, random 20 indices of the total images that we have, I'll just use a simple function provided by NumPy called permutation, random.permutation, and len of x train. So what this basically does is creates a list of numbers with total elements of whatever we have in the training set. So there's 60,000, so but the orders are in random, so we can use this to randomly select. So I'll just assign p first 20 numbers, then plot images x train p, then y train p. Hopefully this will work. Have sublot, okay, not sublot but subplot. Okay, so these are our random, some of the random examples, but the labels, they don't seem nice. Let's increase the figure size a bit, fig size. Let's do it 8 by 8. So 8, I think the figure size is in inches probably, or not. Is this 8 inches? Yeah, whatever. So these are some of the random examples. Now there are two things we need to do before we can use this data into the neural network that we're going to build. So first thing is, our image, each sample is a two-dimensional array or a matrix, but we are just going to make a simple neural network like this. This is called a fully connected neural network, where each neuron or unit is connected to every other unit in the next layer. So here these neurons are input neurons, and these are the output ones. So in our case, each pixel will be an input neuron. So we'll have, because we have image of size 28 by 28, then if we flatten this out into a one-dimensional vector, then we get this 784. So our neural network will have 784 input neurons. Then the layers, hidden layers, will define how many layers we want and how many neurons do we want in each layer. And in the output layer, because we are classifying the digits, and digits are from 0 to 9, so we have in total 10 different categories. So we want each sample to be classified in one of 10 categories. So our output layer will have 10 of these neurons. So given that, first thing we need to do is flatten this 28 by 28 matrix into a one-dimensional vector. So that is fairly simple. We'll use a function called Reshape, which is provided by NumPy. So xtrain train equals to xtrain dot reshape 60,000 10 by what was the number? 784. And similarly for test dot reshape 10,000 by 784. So we could do it like this, or we can just, instead of writing 60,000, we can just say minus one, and NumPy will automatically figure out the actual value that will be used instead of -1. So this -1 means letting the NumPy figure out what should be the number. So based on this thing, this value, we are flattening each into 784 one-dimensional vectors, so it will automatically figure out, okay, I need to replace this -1 with 60,000 and here with 10,000. So xtrain.shape, then xtest.shape. So now we have the data formatted into the way we want. Another thing that we need to do before we can use this data is xtrain.min xtest.max. If we see the pixel value, the minimum and the maximum are from 0 and between 0 and 255. So each pixel, the pixel values, they lie between 0 and 255, but we want the values to be between 0 and 1. Usually neural networks like values between 0 and 1, or a -1 and 1. So we'll normalize the values so that all of the pixel values, they lie between 0 and 1. So for that also we can do xtrain divided by 255.0. So when we divide by 255, the pixels having 255 value will become 1, and the pixels whose value is a 0 will just be 0. So we the values will be between 0 and 1. Okay, that is also done. Now one last thing what we need to do is ytrain.shape. This ytrain is not in the format that we need as well. So because we are doing this multi-class classification, we need the data into different formats. So if we see the first 10, we just see, okay, the values are 504, but we need to encode this into because the output of our neural network contains 10 different neurons. So we also want our label to be a vector of size 10, and only the digit that this particular number represents, so in this case 5, so the only this fifth element will be 1 and rest of them will be 0. This is also called as one-hot encoding, and Keras already provides us with this function. So from keras.utils import to categorical, So whenever you are trying to classify an object into more than two categories, then you have to do this, use this function toCategorical to convert your labels into one hot encoded format. So voidRen equals to toCategorical voidRen, and num classes is 10 because we have 10 different categories. Similarly for void test, we do this. Now everything is fine in that. If we see the shape, we see it's now a vector. Each row is a vector of size 10, and if we see the first element here, you can see only this is 1 and rest of them are 0. So that means this digit is 0, 1, 2, 3, 4, 5. So this is the digit 5. Now we can build a model. So let's import few classes from Keras layers, import input. So this will be our input layer, and dense is the one, the layer that makes this fully connected layer. And we'll also import activation. Yep, that's it. From, and then from Keras.models, import model. So image input equals, let's define our input layer, and its shape is going to be this one, 784. So 784 comma, because this shape expects a tuple, so that's why we just add a comma after this to let Python know that we are specifying a tuple instead of just an integer. Otherwise, if we just do it like this, then Python will think this is just an integer and it will throw an exception. So we just add a comma there. So this defines our input layer like this. So we'll add one hidden layer with let's say 32 units or 32 neurons. So each neuron is this circle as shown in this figure. So now what we need to do is say x equals to tens, and if you see the help, so here we need to specify the number of units or neurons. Units equals to, let's just try 32 for now, and activation ReLU, and for this layer we want to specify the input. So what this means is, this is using this functional API of Keras. So what this means is, for this layer the input will come from whatever this layer computed. So image input, in this case the input layer does not do anything at all. So here we are just getting the value that was here, and we pass it to this layer. So this layer will operate on this input basically. So now we again define another layer. So this will be our output layer. So in this case we will define 10 output neurons, and we want our activation to be sigmoid. About this activation, this is what the non-linearity in neural networks come from. So ReLU is pretty standard these days to use in hidden layers, and sigmoid is used mostly in the output layer, and it makes sense in our case because when we did this one hot encoding, we saw that the values, they were from 0 to 1. So sigmoid activation it produces value between 0 and 1, so it's perfect for us. There's another common one is to use 10x. So if our output value ranges from -1 to 1, then we should use this 10x. Otherwise, for this for our purposes, it's a sigmoid is fine. And for this layer to the input for this layer comes from the previous layer. In this case, the previous layer is just x. Whatever this layer computed and stored in x, this will come as an input for this layer. Whatever this layer, this highlighted layer computes, then it will again be stored to this variable x. So this is all. We define an input layer, hidden layer, and then output layer. So now that we have our layers ready, we can build a model equals to model inputs equals to input, outputs equals to x, and we can just use this summary function to see the details. So again, the same thing, so it will show what layer produces what kind of output. So in this case, it will just produce a output of vector of size 784, and this none means the batch size. So instead of giving each of the samples one by one, we'll just give the neural network let's say 128 images at a time. So because it's more efficient to do it that way. So this none just means that we could pass any number of examples during the training or during the evaluation. So yeah, this is not known right now, that's why it's known, but yeah, these values are the ones we're generally interested in. So in total, our neural network has 25,480 parameters. Now there's two more steps to fully train our model. First thing is to define how we want to train our model. So this is done by using compile function, and there are a few things we need to specify. First one is optimizer, and use the common ones are Adam or SGD and SGD or RMS prop. But yeah, for this one, let's try this Adam. Then next one is we should specify what kind of loss we want, because we are trying to classify more than two categories. We need to use this loss function called categorical cross entropy. You can look into Keras website for different available losses and these optimizers for more details. But yeah, after that, when training, we want the Keras to show what is the accuracy. So we'll just specify in metrics as a list accuracy. So this is all we need to specify in order to make our model, in order to tell Keras how to train our model. So now we can finally train, and this is done by calling this fit function, and here we need to pass the training data and the labels. Then batch size, we'll just pass 128, so it means that we have 60,000 images in our training set, but at one time we'll only give 128 images for the network to train, and then after it's done with calculating this loss and all, and then we again take the next 128 images, then until all of the 60,000 images are done. So when all of those 60,000 images are done, one epoch is considered to be complete. So I'll just say we'll train it for 2 epochs. That means we'll go through all of these examples, 60,000 example, 2 times. And is there anything else? Okay, well, we're at let's say validation split. We'll also say that reserve 20% of our data for doing this validation, and we can train now. So you can see the loss is decreasing, our accuracy is, this is the training accuracy, and this is the loss and the accuracy on the validation set. So this is on the 20% of the data that we told Keras to reserve from this training set. So in our validation set we get 93% accuracy. So let's again run this. Let's try for 6 more. So you can run this again and again, because it won't start from the beginning, because it already has trained for how many epochs you specified before. So it seems that we are stuck at 95% accuracy, probably because our neural network is too small. We just have 32 neurons in the hidden layer, and we have only one hidden layer. But let's just continue with the evaluation of the model on the testing set. So there's a simple function called this evaluate, and here we can pass our test set, and again the batch size 121. Anything else? No. Okay, this the output might be confusing, so you can just do model dot metrics names. So this loss, this loss, so this is the loss, and the second metric name is accuracy, so this is the accuracy. So in our test case we have 95.83% accuracy. So let's try to increase the number of neurons in the hidden layer. I'll pump it to 128, and if we run it again for 6 epochs, okay, we're at 96, and yeah, it increased a little bit. So usually the loss should be decreasing with every epoch, and your accuracy should be increasing, and the validation loss and the validation accuracy as well. So let's make some predictions and then see how it went. So predictions equals to model.predict, then we just have to give our test set and batch size with 128. So if we look at the shape, then it's in the same format. So each prediction is a vector of size 10, and if we look at the first example, so these are all probabilities. So the class, the digit, the input that is the digit or the image that we want to predict has the highest probability. So in this case we need to do argmax, and x is equals to 1. Yep. So what we did was we selected the index of the probability number that was the highest. So in this case the first digit it seems is digit 7. And let's check with white train, because we converted this into one hot encoder. Let's convert this back to our normal format, so argmax, and let's just check the first 10 classifications. Okay, seems very wrong. Import classification report. Aha, not white train, but this should be white test. White test. So it looks pretty good, and what I was trying to do was this scikit-learn has this function called classification report, and it gives us more information rather than just this the accuracy percentage. So what we need to pass there is the actual label and the predicted the whatever our model predicted. So print white test print. So this gives us more information. So these 0 to 9 are the categories, and for each category this gives us the precision, recall, F1 score for each of the categories. So it's better to have both of these number high. In some problems this might not be possible, so you have to either try to increase the recall and sacrifice the precision, or there are some problems where you might want to sacrifice the recall and increase the precision. But in our case it seems to be doing really good. We have both average precision and recall of 97, so that's pretty good. So in this tutorial we just built a simple neural network. This is called fully connected neural network, and we managed to achieve 96% accuracy in our testing set as well. In the next post we'll build a convolutional neural network and increase the accuracy up to 99%. So see you next time.